Without any further ado, I would like to introduce our first speaker of the day, which is Dan Molzahn. He is an assistant professor in the School of Electrical and Computer Engineering at the Georgia Institute of Technology, and his research interests are in power system optimization, particularly in dealing with power flow nonlinearities. And he will present us a new term named Balancibility, and this is on the existence and uniqueness of power flow solutions under voltage balance requirements. Dan, you have the floor.
Great, thanks, Dirk. Yeah, so this is a new term. We are trying to coin a new term with this paper. So I first want to mention that this was work that I intended to have presented by my former postdoc, Bowen, who's at Argonne National Lab. Unfortunately, Bowen got sick after doing all the work making the slides, the bulk of the work making the paper. He ended up getting sick yesterday, and so you're going to hear from me instead. The title of the presentation is Balancibility, Existence and Uniqueness of Power Flow Solutions Under Voltage Balance Requirements. And the idea here is that we want to leverage existing power flow solvability conditions, which are conditions that guarantee the existence of a power flow solution under certain parameter ranges. And we want to extend these conditions to handle the situations that are appearing in distribution systems. And in particular, want to be able to enforce voltage balance requirements inside these power flow solvability conditions. So I'll get more into what I mean by that in a minute, but a lot of the sort of motivation behind this is to be able to do robust feasibility analysis and robust optimal power flow problems. Okay, so what do we mean by voltage unbalance? So we operate our distribution networks in such a way that we want to have a balanced set of voltage phasors where the voltage magnitudes are equal and voltage angles are off by 120 degrees. So we're in this situation. But that might not always occur. We might have unbalanced operation where the voltage magnitudes are not equal or the phase offsets are not 120 degrees. And this is increasingly a problem when we have power injection variability because we get time varying voltage unbalances among these voltage phasors. And this can have some pretty significant negative impacts on power systems and the individual components within them. So especially when you have large induction motors, where the amount of voltage balance determines the losses, or it can increase the losses in the motor. And so even when you start getting up around 2–3% unbalanced, the increase in the losses of the motor can be around 10 to 20%. And this is problematic because this causes the motors to burn out early. And so there's a few different methods that people use to quantify phase unbalance. There's three common definitions. The first is what's called the phase voltage unbalance rate, or PVUR. Essentially what this does is it looks at the largest deviation from the average in terms of the line to ground voltage magnitudes. So larger deviation from average means a larger amount of voltage unbalance. There's a similar definition for what's called the line voltage unbalanced rate. This is used by NEMA and a lot of the motor standards. It's similar to this phase voltage unbalance rate, except it uses the line-to-line voltage magnitudes instead of the line-to-ground voltages. The final definition is probably what you're most familiar with from your power system undergraduate classes, where it's called the voltage unbalance factor, VUF. This is an unbalance that's defined in terms of the sequence voltages, so the positive, negative, and zero sequence voltages. Comes in two flavors. We've got the negative sequence voltage unbalance factor, which is the magnitude of the negative sequence voltage divided by the magnitude of the positive sequence voltage. We've also got a similar version for the zero sequence voltage unbalance factor, which is the zero sequence voltage divided by the magnitude of the positive sequence voltage. And if you want all sorts of gory details and mathematical comparisons between these different definitions, I refer you to this paper here where we go into a lot more analysis of comparing these. And so what are these power flow solvability conditions that I mentioned earlier? So what people have spent a lot of time, and there's been quite a bit of work on this recently, developing are sufficient conditions on the power injections which guarantee that there exists a power flow solution. And then in some cases, you can show that that solution is unique. So you give me a set of power injections, I go away and I run Newton-Raphson, I solve the power flow equations. Great, I know there's a solution for that point. But if I want to show that there's a solution for a range of operating conditions, that's less straightforward. And that's what these conditions are intended to ensure. And so this is, what these conditions will give is a sufficient condition for power flow solution existence. They also will tell you, at least in some cases, a region in the voltage space that contains those solutions. So here's a range of power injections. It'll map to a space in the voltage space, and we can characterize that space. We want to extend these conditions to be applicable to distribution networks, in particular by incorporating voltage balance requirements into those conditions. So what does this look like graphically? So imagine we have some set of uncertain power injections over here. This is maybe the range of wind and solar generation that might occur. What we want to show is that all the solutions within this set map to some different set in voltage space. And that's what these existing solvability conditions show, is that there exists a voltage space solution for each of the uncertain injections. What we additionally want to add is that to show that these solutions also satisfy a voltage unbalance requirement, that they're all within the voltage limit or the unbalanced limits. And so we want to show a unique power flow solution exists within the voltage magnitude limits and that these voltage requirements are satisfied. Okay. So it's not a PSSC talk without at least a little bit of mathematics. And so I want to go into a high level sketch of our derivation behind these solvability conditions. So what we start from is a solvability condition that was developed by one of the co-authors, Bai and Andy Sun. And what they showed is that you can derive a powerful solvability condition that's parameterized by the power injections. So for a given set of uncertain power injections, these constants C and R are parameterized by that uncertainty set. And what these conditions show, what Bai and Andy showed, is that all the voltages within that uncertainty set will lie within these disks. These conditions here define a set of disks in a complex space. This applies for either radio or mesh topology networks, but you do need to have a single slack bus with the rest of the buses being Y-connected PQ buses. So there's a little bit of a limited application in terms of the solvability condition, but you can derive this condition. And what we're going to do is build on top of this a chain of guarantees where we can say that the solvability condition guarantees existence and uniqueness of a power flow solution. We're going to add on a voltage balance condition as well. And so these become increasingly conservative because we have the conservativeness of the previous conditions that we build on top of. But in general, this is generalizable to other classes of system models. Our conditions don't require the same conditions that the solvability condition here, the power flow solvability condition relies on. Okay. So to continue this derivation, what we're going to do is we omit the balanceability conditions for the first two phase unbalance definitions, PVUR and LVUR. They're fairly straightforward due to their linearity, but you can see the paper for some more details. We're going to go into a bit more depth in this voltage unbalance factor, and in particular this voltage unbalance factor that looks at the negative sequence voltage magnitude divided by the positive sequence voltage magnitude. And so that's this definition here. What the phase unbalance requirements say is that the voltage unbalance factor has to be less than some threshold, epsilon. So less than, say, 2% voltage unbalance. If you do a little bit of arithmetic here, what you can do is square both sides of this, and then you can rewrite the voltage phasor, or the squared voltage magnitudes, as the product of the voltage phasor and its complex conjugate. And so this allows you to rewrite this phase unbalance requirement in this, this form here. And then what we essentially want to say is we combine this with the power flow solvability condition. And what we want to certify is that for all the power injection, or for all the voltages that are within these disks that are identified by this power flow solvability condition, that the largest amount of phase unbalance will satisfy this limit. And so mathematically rewriting that, we can say we want to show that the maximum value over all these voltage phasors that come out of the solvability condition satisfies this condition. And so if you stare at this for a second, what you realize is this is a non-convex, quadratically constrained quadratic program with multiple constraints because we have these constraints from the disk. And so this is where the kind of conceptual difficulty comes in. And we have three different methods for dealing with this non-convex QCQP. The first one is to simply bound each of the individual components. If you look at this here, we're maximizing this magnitude, which we can try to upper bound that. And we can split this second term here. We're maximizing a negative quantity, and so we can bound that by minimizing it. And so if we can compute bounds on each of these individual quantities, then we can get a valid bound on this quantity here. And so Bowen goes into a good amount of detail in the paper on how you can prove bounds on these components. Okay, then the second component, or the second approach that we propose is to use the polytope approximation. Essentially what we can do is we can take these disks and outer approximate them with polygons and get a conservative approximation to the solution of this non-convex QCQP. As we increase the number of edges in this polytope, we can show that we approach the solution to the original non-convex QCQP Bowen has a nice theory in the paper showing that the solution to the non-convex QCQP will be on the boundaries. And so you can show that this polytopo will give us a conservative estimate of the solution. The third method is to apply relaxations to this problem. So we want to get a conservative bound on this non-convex QCQP. Well, we can use Lagrangian relaxation or semi-definite relaxation and apply it to this problem. Turns out we can show in this specific problem that these relaxations give the same optimal value. And we can also show that under certain conditions, that value will be the exact solution to the original non-convex QCQP, meaning in those cases, our condition is not conservative. It's necessary and sufficient, not just sufficient. All right, how does this work in practice? Well, we applied this to a few different situations. And what we're showing here is the optimality gap on the vertical axis. So this is this true solution to this non-convex QCQP relative to the solution to our approximated version, our conservative approximation of the problem. And so this tells us sort of how conservative our condition is always sufficient to ensure powerful solvability and balanceability. This tells us sort of how close to being necessary and sufficient it is. What we can show here is this was a case where the Lagrangian relaxation or semi-definite programming relaxation of this QCQP was not exact. There was a small optimality gap, but as I said, this optimality gap was small. What we're showing as you go along this x-axis is the number of segments that you have in this polytope approximation. You can see that as we increase the number of segments, we approach the solution to this non-convex QCQP, meaning that our condition for balanceability is close to being, and the limit becomes the true solution. It's not conservative in that sense, or it's conservative, but it's no more conservative than it has to be. Whereas this approximation by Bowen sort of does okay, but not good. Here's another example where these optimality gaps were much smaller. In this case, the SDP and Lagrangian relaxations gave the exact solution to satisfy the condition that we needed to have that happen. And again, as you increase the number of edges in these polytopes, we approach the solution to the problem. And so again, our conditions are always conservative. They always guarantee that we'll satisfy the phase balance requirements and the power flow solution requirements. Thanks, Dirk. But this tells us how conservative. We applied this to a case study. We took a 5-bus system out of this paper by Molly, Ian, and Johanna. We had a critical bus out here where we had a motor that we wanted to maintain phase balance at. We had a load that was unbalanced, and this parameter K here tells us how unbalanced. You increase K, you get a more unbalanced loading condition. What we're showing in this figure here is as you increase the amount of unbalance in this load, how much unbalance is there at this critical bus 4. What we see is that as you increase K, the unbalance at the critical bus increases, but our bound does a pretty good job of actually capturing the amount of unbalance. It's not too conservative. So to wrap up here, I told Dirk to be strict on time, and so he's going to cut me off, is that we derived this and assessed this balanceability condition. We derived this for a whole bunch of different voltage magnitude unbalance, or voltage unbalance definitions. We also have strong theoretical guarantees, and we can show it's not too conservative. In our future work, we're trying to test this on larger networks with a larger amount of variability. We also want to extend these solvability conditions where we can apply this to more general networks, not just Y-connected PQ buses. And we also want to apply this to our main motivation for this work, which is robust AC OPF problems. So again, I want to thank my co-authors, thank Dirk for chairing the session, and look forward to any questions you might have.
Yes. So in the meantime, thank you very much, Dan, for this excellent presentation and keeping your time. Good example for the rest. I would like to ask to use the Q&A session. I didn't make it very clearly. Okay, where the first question is actually coming from Mats. How does a balanceability relate to maximize voltage margins ability? Can you comment on that one?
That's a good question, Mads. It's certainly not as catchy of a name. That's for sure. So if I'm understanding your question correctly, I think what you're asking is, do these conditions also include the voltage margins, or do you basically, are these conditions sort of restricting yourself to not go too close to the solvability margin of the system? I guess I'm not 100% sure what you're asking. But in what I can say is that our conditions do, the existing solvability condition does build in voltage magnitude bounds. And it seems that it does a reasonably good job. We in fact tend to be mostly limited by the solvability condition that we're imposing. So it's not necessarily the balanceability condition that's the issue. If we have less conservative solvability conditions, we can do a better job.
Okay, then we have another question, which reads, great work. Conservativeness is crucial to estimation based on solvability condition. How do you deal with or control conservativeness?
Right, so we definitely wanted to have these conditions be sufficient, not necessary. We were interested in ensuring that these conditions, if you want to use this in a robust problem or robust feasibility evaluation, you need it to be conservative. And so what we did is we came up with a kind of different approaches. I mentioned these 3 different approaches for handling the conservativeness of the problem. And there's essentially these different approaches set up a trade-off. If you want to invest more computational time, you can solve the non-convex, you can solve an STP relaxation, or you can solve this polytope outer approximation with lots of segments. But then that limits your computational tractability. Whereas on the other hand, you can be less conservative, more conservative, not as accurate, and have a more computationally challenging problem. Less computationally challenging problem.
Okay. Okay, very good. And then we have one more question coming up, and I think then we'll have to move to the next one, unless there is a burning question. Oh, I see another one come. We'll try. Dan, you need to be short on these 2.
I'll answer fast. Yeah.
Yeah. Okay. In case of modeled PQ bus, can we consider reverse flow with DG as negative load?
I'll be fast. Yes.
Okay, done. Thank you for being fast. And the last question then, thank you for the very nice presentation. Very interesting. A slight more general question. Do you know if these sorts of techniques work well with 4-wire circuits? I have seen some works that suggest that 4-wire circuits are much more likely to have multiple feasible, reasonable solutions, and wondered if losing uniqueness mattered. And that's what
that's a very interesting question. Yeah. So we didn't, and this would be a better question for Bowen. Unfortunately, he's not here right now. But I know we didn't try it on 4-wire circuits, or I don't believe that he had tried it on 4-wire circuits. But you raise a really interesting point that if you are curious about this, maybe shoot me an email, or I'll follow up with you afterwards. I think it's a really interesting point that we haven't explored enough in depth.
Okay, so that's an excellent close to this presentation. Thank you very much, Dan, for that. In the meantime, I'll open up my